The Heisenberg's uncertainty is probably the most ironic, coolest and saddest concepts of modern physics. The uncertainty principle states that it's impossible to know simultaneously the exact position and momentum of a particle. Well, starting from the bottom, an uncertainty is due to the impossibility of knowing everything precisely. It's nothing more than a range or an interval of the measured value. Why are uncertainties so important? Well, quoting from a professor of mine, only uncertainties can be measured. Basically, an uncertainty tells you how successful, or in my case, unsuccessful, your experiment was. So regarding this mysterious particle, its uncertainty appears because it behaves both as particle and wave simultaneously. Isn't this a crazy idea? Considering classical mechanics, it is possible to know the exact position and speed of a particle. A wave, on the other hand, is a disturbance in space with one important property, its wavelength, which is the distance of a complete cycle. Due to its nature, it's not possible to assign a position. In considering a point on the wave, there's a high probability to find it in different places, such as on the peak, the valley, or somewhere in between. The wavelength is essential to quantum physics because it gives the momentum of a particle. Momentum can be seen as the amount of energy a particle brings with itself. High speeds correspond to short wavelength and great momentum. Low speeds correspond to big wavelength and small momentum. Think about it. Two cars have the same mass, but one of them has a considerably greater velocity than the other one. Which one has more energy in itself? Now consider this. A wave has a wavelength and therefore a momentum, but no particular position. A particle, on the other hand, has a position but no wavelength, because obviously it is not a wave. What is the solution? A quantum particle that has both position and wavelength, which allows it to have a momentum. What are the cons? It doesn't have only one position and a wavelength, but quite a few of them simultaneously. How? Due to the principle of superposition, which states that when not observed, and when not observed only, a particle may be in different places with different speeds simultaneously. So say we are hardcore and choose to observe this quantum particle. There is a limit to be precise on its properties, again, in momentum and position, which is given by the Heisenberg's uncertainty equation. If we are great lab geek workers, the smallest uncertainty will be Planck's constant divided by 4 pi. Now check this. If we are really interested in the particle's momentum, we can diminish its uncertainty to have a more accurate value. But the growth of the position's uncertainty will be inevitable. It is really a matter of what we want to know best and what we are not bothered to really know. Full accuracy is not really a physicist's characteristic. In summary, a quantum particle is a duality of nature, an assigned position and a momentum. The uncertainty of Heisenberg appears due to the principle of superposition. The position and the momentum's uncertainties have a relation of inverse proportionality. There is a limit on every measurement, a limit on our knowledge.